All right, we're going to get into our second moment distribution example, and it's going to be the same directions as before. We're going to draw the shear and moment diagrams. And in this example, I'm going to go a little faster. I'm not going to go into as much explanation on certain aspects of this because I'm assuming you watched the first video already. So we have a beam here. And it's fixed at A, and then we have 3 roller supports here. So we've got a roller at the free end, that's going to be D actually, and then we've got 2 evenly spaced in the span. So we'll have one right here, and then we'll have another right here. Draw that a little bit better. Okay. And this is B and C. And there's not supposed to be a gap there. I'm just, my artistic skills are just not good. So in AB, this is 30 kips. And in BC, we've got 40 kips in the middle of each of those spans. So if we put a dimension line, I'm very bad at drawing straight lines on this device. So if we put dimension lines here, we're going to have 15 feet, 15 feet, 15 feet, 15 feet, and then 30 feet. So, and then we have a case of EI is constant for the entire member. All right, so the first thing we want to recognize when we write the solution is this is indeterminate to what degree? Should be indeterminate to the 3rd degree. We have 3 reactions here, 4, 5, 6 reactions total. We have 1 member, so 3 times 1 is 3, and then 6 minus 3 is 3. So it's indeterminate to the 3rd degree. The next thing we want to do is go ahead and calculate our member stiffnesses. So I'm going to use the relative stiffness. I mentioned in the last video you could use, if you have EI as constant, so long as EI is constant, you can use either relative stiffness or the regular stiffness calculated as 4EI over L. So long as EI is constant for the whole system. You drill that into your heads. So I'm going to use relative stiffness, okay? So I'm going to say K rel AB is 1 over the length of AB. And of course, that would just be 1 over 30 feet. And then similarly, K rel BC is also 1 over 30 feet. And then K rel CD is also 1 over 30 feet. All the spans are 30 feet long. Now we need to get our distribution factors. Okay, now question, how many distribution factors do we have per span? Do we have 1 per span? No, we have 2 distribution factors per span, 1 relative to each end, okay? So make sure you know that 2 distribution factors per span, 1 relative to each end. So the first thing I'm going to have is distribution factor AB, that's in the span AB, but relative to A, okay? So when we crank that through, it's the stiffness of the span you're in this case AB, divided by the sum of the stiffnesses, at A, okay? So that would be KAB divided by KAB plus infinity. Infinity is coming from the fact that it's a fixed connection. So this is 0. Then we're going to have a distribution factor BA. Now we're still in the span AB. So the numerator is still KAB. Okay, remember, this distribution factor, we're still in the span AB, but it's like we're infinitesimally to the left of B. Okay, so what all's coming in at B? We would say sum of the stiffnesses at B. So it's KAB divided by KAB plus KBC, right? Because member BC is connected at B. All right, so when we crank this through, we of course get 1 over 30 divided by 1 over 30 plus 1 over 30. And when you punch this through, you should get 1/2 or 0.5. And then we're going to have a distribution factor BC. So we're in span BC now. We're in span BC, but we're relevant relative to B. So we're infinitesimally to the right of B now. That's one way to think about it. So we would say KBC divided by KAB plus KBC. So ask yourself again, what is connected at B? AB and BC. So when you crank this through, you again get 1 over 30 divided by 1 over 30 plus 1 over 30. And so I get 0.5 here. And then we're going to get distribution factor CB. Okay. We're still in the same span of BC. We divide by KBC. And then what else is connected at C this time? So again, we're right here. What's connected at C? Well, CD. So we would say plus KCD. And when you crank this through, you'll get 1 over 30 divided by 1 over 30 plus 1 over 30 equals 0.5. And then we're going to get distribution factor CD equals KCD over what's connected at C. Well, BC is connected and CD is connected. So we would say KBC plus KCD, and we'll get 0.5 for that. And then the last one is distribution factor DC. And so we get KCD divided by KCD plus 0. That's a roller that's an end span roller. So we get 1 here. Okay, the next thing we're going to do is we're going to quote unquote fix all spans and compute fixed end moments as if each span was fixed. Okay, so I'm gonna go ahead and crank this through kind of quickly. You want to make sure you know you're using PL over 8 for the first 2 spans. So fixed end moment AB, if we use PL over 8, that was 30 kips times 30 kips times 30 feet divided by 8. I get 112.5, but that should be a negative. Remember, fixed end moments are reactive. Kip feet, okay. And then we're going to get FEM BA is a positive 112.5 kip feet. And then FEM BC is negative 150 kip feet. FEM CB is a positive 150 kip feet. And notice the last span CD does not have any loading on it, so there are no fixed end moments in CD. Okay, so you can write that down. FEM CD equals FEM DC equals 0 because we have no loading there. So at this point, we're about ready to make our table, okay, just like we did in the last example. So I'm going to kind of spread this out, and let's see how much room we have left on this page. And that should be enough. So we're going to have a fixed connection here. There's A, and Spread that out so we have a lot of room. There's our roller at D, and evenly spaced out. That looks pretty evenly spaced out. There's B. There's C. There's my 30 kips. There's my 40 kips. And EI was constant for all the members. Let's go ahead and put our dimension lines here. Okay, now the next thing I like to put is a stiffness, like a row indicating the stiffnesses. So, and again, we can kind of put dashed lines all the way down to help us, create a boundary for our table. So I use the dimension lines to help me just shape up that table. Okay, if we have to go a little farther down, I guess we can go just a little bit farther down. I'm trying to keep this on this page and not cross over to the next page. So this K value is, we use K relative, so we could put K rel here. 1 over 30, 1 over 30, and 1 over 30. And then we have our distribution factors, okay? So if we make a little row for our distribution factors, we have a 0 here, we had a 0.5, we had another 0.5, we got a lot of 0.5s here. We need to make sure we know which 0.5 is which later on. And then we have our FEMs, our FEM values, negative 112.5, positive 112.5, negative 150, positive 150, 0, and 0. And over here, I'm going to put my units kip feet here. Okay, so here are my FEMs. Now, try to make a nice little row here. So then the question is, where do we have an unbalanced moment? Okay, remember, we want to find a point where we can recognize we have an unbalanced moment, and we need to figure out how to go about that. Now, there are multiple starting points, okay? So different people may start at a different point if you have unbalanced moments in a few different spots, okay? So let's talk about this. First, as of now, do we have an unbalanced moment at D? Well, no. We have a moment of 0 at D, and we should, because at an end span roller, that means the roller is at the end of a member, we should have a moment of 0. So we're good. What about the fixed connection at A? I guess I forgot to label that. I should put an A there. What about the fixed connection at A? Well, remember, a fixed connection can handle any moment you throw at it. So even though we got a negative 112.5 at A, that's okay. That's okay. What about B and C? Well, check this out. B and C, there are 2 points there that we have an unbalanced moment. At B, we're saying that infinitesimally to the left of B, we have a clockwise moment of 112.5, and then infinitesimally to the right of B, we have a counterclockwise moment of negative 150. That is incorrect, okay? We should have the same magnitude moment infinitesimally to the left and infinitesimally to the right of B, but right now we don't. So B is unbalanced. And similarly, A is also unbalanced because we're saying we have a clockwise 150 infinitesimally to the left and then 0 infinitesimally to the right. So right now, as it is now, it looks like B and C are trying to roll off the page. Okay, they're unbalanced. So we need to start at either B or C, okay? And it doesn't matter which one you start at. You can start at either B or C. Now, depending on where you start, it may cause you to have extra iterations of this process. So you want to get to a point where you've done enough of these problems to where you can start strategically. I say we need to start at B with this lack of balance. And the reason why is because if we start at C, we immediately will do one iteration and kick some moment over here to this roller that really should stay 0. Okay, now that may happen anyway, but I'm not gonna, say let's do that right out of the gate. All right, so we're gonna start with the unbalanced moment at B for our calculation. So I'm gonna roll down here just a little bit. This may be a good idea to get an extra sheet of paper and do your scratch calculations on balancing things on a separate sheet of paper, okay? So I'm going to say I'm going to come down a little bit, unbalanced moment at B, and that is equal to 112.5 kip feet, okay? Is that it? No, it's 112.5 kip feet minus 150 kip feet. And so the unbalanced moment is actually negative 37.5 kip feet. Okay, remember at B, you've got this clockwise positive 112.5, and you've got this counterclockwise negative 150. So the imbalance is them together, right? So when you numerically combine them together, you get a negative 37.5. That is the unbalanced moment at B. Okay, now what we do is we multiply the negative of that unbalanced moment, multiply the negative of the unbalanced moment by the distribution factor at B, or the distribution factor BA, okay? So we're going to multiply it by the distribution factor BA. So, trying to scroll here. So what we have is distribution factor BA times the negative of that 37.5, which is positive 37.5 kip feet. And distribution factor BA is 0.5 times 37.5 kip feet, which gives us a positive 18. It's like 18.75, so I'm going to round that to 18.8 kip feet. Okay. Now, what are we going to do? We're going to put that 18.8. That 18.8 is going underneath this value right here, 18.8. Okay, so we're good so far, right? Almost. The next thing we need to do is we need to put an 18.8 somewhere else. We need to then say distribution factor BC times 37.5 kip feet, which is the 0.5 on the BC side times 37.5 kip feet. And this also happens to be 18.8 kip feet. Okay, so 18.8 also goes here, 18.8. Now, here's where you got to be careful, okay? The first 18.8 I calculated here was calculated using this distribution factor, okay? Distribution factor BA. The second 18.8 kip feet was calculated using distribution factor BC. All right, so they happen to all be 0.5 now, all right? Maybe I made up this problem unwisely by having all the same numbers, but make sure you know which 0.5 is which. I mentioned that earlier. So then what we do is we got to carry over a portion of each of these moments, right? So we'll make a note here. We're going to say carry over a portion of these moments to the adjacent supports. All right. Now remember, a carryover factor, a COF carryover factor, we're always using that as 0.5. Okay. Now here's where I want you to be careful. That carryover factor, that is a different 0.5. That is yet another 0.5. We're always going to use a carryover factor of 0.5 for our purposes. Okay, so this 0.5 is not the same as these 2.5s. And in fact, these 2.5s are not the same as each other. Those are all distinct different 0.5s. So here's what we're going to do. We're going to say 0.5 times 18.8 kip feet is equal to 9.4 kip feet to carry over to A. And then, so this, let's use different colors. This 18.8 is this 18.8, okay? And then we're going to say 0.5 times 18.8 kip feet equals 9.4 kip feet to carry over to C. So this 18.8 is this one, all right? So I'm going to use some color coding here to help us out, help us make sure we know what we're looking at. So here's my green, 9.4. And then this was my purple, 9.4. I promise I'm not sick. It's 100% allergies. I've been outside a lot today. Okay, so what do we do next? Well, at this point, check this out. At this point, B is balanced. So you can put a little underline underneath it. B is balanced, right? How is it balanced? Well, when we took this difference right here, we got to a negative 37.5. And then if we add in positive 18.8 to both sides, that wipes it out. So we have a net moment at this joint of 0. Fantastic, right? Net moment of 0 at this joint. If you sum vertically here and you sum vertically here, you will get a net of 0. So let's just test it out real quick. If you do 112.5 plus 18.8, you get 131.3. And if you did negative 150 plus 18.8, what do you get on the other side of that? You get, well, negative 131.2, but that's round off error. So net 0 right here. And now we're ready to move to C. Our next unbalanced moment is at C, okay? So this is that iterative process. So here's our next calculation. We have an unbalanced moment at C. And what is that equal to? Well, now that's equal to 150 kip feet plus 9.4 kip feet. That gives us a total imbalance of 159.4 kip feet at C, okay? So what do we do about that? We multiply the negative of the unbalanced moment by distribution factor on either side of C, okay? So I'm going to say distribution factor CB times negative 159.4 kip feet equals 0.5 times negative 159.4 kip feet. And when I crank that through, I get negative 79.7 kip feet. Okay, so that negative 79.7 goes goes underneath the side on the just to the left of C. Okay, so we put here negative 79.7. Okay, and again, the distribution factor we used was this value. Now we do the same thing, but on the other side. Okay, so we're gonna scroll on back down, and we're gonna say distribution factor CD times negative 159.4 kip feet is 0.5 times negative 159.4 kip feet, and we get negative 79.7 again. Now, where does this get placed? Well, this value is on this side, negative 79.7, and the 0.5 distribution factor we used was this value. So what do we have here? Well, we have a net balance. That's great. We have a net balance. But remember, half of each of those moments has to get carried over, right? Half of this moment needs to get carried over in this direction, and then half of this moment needs to get carried over in this direction. So let's do that, all right? That's our carryover calculation, which again is a different 0.5. So we have 0.5 carryover factor times negative 79.7 kip feet. And when we crank that through, we get negative 39.9. I'm doing some rounding here. Kip feet to carry to B. And then we have 0.5 times negative 79.7 kip feet. Again, happens to be the same number, 39.9 kip feet to carry to D. Okay, so we gotta again be careful with each of these, what each of these values means. Okay, so I'm gonna say going in this direction, we have negative 39.9, and then carrying over in to the right to D, I'm going to use that purple color again, negative 39.9 over here. Okay, so the green value is this value, oopsie, is this value, which corresponds to what happened in CB right here. And then the purple value is this number, which is corresponding to what got sent over to D from the span CD at C. Okay, so be careful with all this. Our next example will have different distribution factor values, so it may be more clean to see. But we keep going. The next question is, where do we have another unbalanced moment? Well, if we look at this, what did we just do? We actually just caused another imbalance at B. So we're kind of like, ooh, we caused an imbalance at B. We definitely caused an imbalance at D because D should have a net moment of 0, and now it doesn't. So let's go to D now. Okay, let's go to D and address the unbalanced moment that we just introduced at D. Unbalanced moment at D. Okay, now this is equal to that negative 39.9 we just sent over there, kip feet. Okay, and now check it out. We say distribution factor DC times the negative of that value, which becomes a positive 39.9 kip feet. Distribution factor DC was 1 times 39.9. So we're saying that 100% of that moment better be sent away. All right, better be balanced off. So this obviously is positive 39.9 kip feet. And then I'm going to go ahead and do my carryover calculation. I'm going to carry over half of that. So remember that this 0.5 right here is my carryover factor. Carryover factor times 39.9 kip feet, which comes out to be, I'm just going to round that to 20 because 39.9 is almost 40. 20 kip feet is carried over, say, to carry to C. Okay, so what does our table look like now? What does our table end up looking like now? We would say 39.9, and then half of it says balanced, half of it gets sent back over to C, and that's an amount equaling 20. 20 right there, okay? So now D is balanced. We're good on D, but now both C and B are imbalanced, all right? So we're going to have to do this a few more times. Let's go to B next. Let's say, let's look at that unbalanced moment at B. That unbalanced moment at B is equal to negative 39.9 kip feet. Okay, look at it on your paper. And then what are we going to do? Well, we're going to say distribution factor BA times the positive of that, times 39.9 kip feet. Distribution factor BA was 0.5. So that gives us, I'm going to round that and say 20 kip feet. And then we're going to say distribution factor BC times 39.9 kip feet is also 20 kip feet. And then we got to carry over, right? Carry over. So we're going to say 0.5 times 20 kip feet is 10 kip feet. To carry to A. So again, this 20 right here corresponds with this 20 to carry to A. And then 0.5 times 20 kip feet is 10 kip feet to carry to C. So this 20 kip feet corresponds with that 20 kip feet to carry to C. So let's go to town on that. The two 20s that I first calculated would go, one would go here and one would go here. So this is balanced, okay? And then we said half of this 20 gets sent over to A. So this is 10 right here. And then we said half of this 20 right here gets sent over to C. So there's our 10 right there. I think I used the wrong color on that 20. I'm sorry. I'm just changing colors here. Don't panic. Don't panic. 20. There we go. Okay. So so now B is balanced. We're good. We're good on B. What's not balanced now? Well, C is definitely not balanced. C is not balanced. We have an imbalance right here. Okay, right? If you added up all these moments vertically down, you would have them not equal 0, and they should have a net value of 0. So we're going to go to unbalanced moment at C. Unbalanced moment at C. Okay, so what is that equal to? Well, that's equal to 10 kip feet plus 20 kip feet, which is 30 kip feet, okay? And then we're going to distribute that. So we're going to say distribution factor CB times a negative 30 kip feet gives me a negative 15 kip feet. And then we're going to say distribution factor CD times negative 30 kip feet, again, gives me a negative 15 kip feet. We're going to carry over 50% of each of those to their adjacent reactions. So we say carryover factor is always 0.5 times negative 15 kip feet equals negative 7.5 kip feet to carry to B. So going with our color coding, this negative 15 is this one. And then we've got 0.5 times negative 15 kip feet equals negative 7.5 kip feet to carry to D. So where'd my color coding go? So this negative 15 corresponds with this negative 15. So scrolling on up back to my table that I'm populating, I'm gonna put my negative 15s here that I just calculated. That's what balances off C, is balanced now. And I've got half of the negative 15 just to the left of C gets sent over to B as negative 7.5. And then half of the negative 15 that's to the right of C gets sent to D as negative 7.5. So now, what have we just done? We've just unbalanced D again, and we've just unbalanced B again. So you may be thinking, well, what are we doing here? I mean, this just keeps going back and forth. I keep balancing one thing, and then I take something else out of balance. Well, if you notice the unbalanced moments, what are they doing with every iteration? They're getting smaller, okay? So these unbalanced moments are getting tinier and tinier with every iteration until eventually they're going to approach zero, all right? So this is just several iterations that we just have to go through until we have a close to zero unbalanced moment, okay? So here's what I'm going to do next. I'm going to go to my unbalanced moment at D. Unbalanced moment at D. And that's equal to negative 7.5 kip feet. And then we're going to say distribution factor DC times the positive of that, or the negative of it, which is positive. So I get a positive about 3.75. So I'm going to round that to 3.8 kip feet. Okay. And then what do we do with that? We send half of that over. Let me check my calculations real quick. I think I may have. No, we're good. I wrote something down wrong for my notes. This is 7.5. Yeah, because distribution factor DC is 1, right? This is 1 right here. We're good. And then we carry over half of this. This 0.5 is my carryover. 7.5 kip feet. There's the 3.8 kip feet to carry to C. Okay, so scrolling back up here and populating that portion of my table, I've got this balanced off as 7.5 again. I like to put a little line underneath it of some sort. And I've sent over here half of that, which is 3.8 kip feet. Thereby causing another imbalance at C. Okay, but we'll worry about that later. So let's look at that imbalance at B right now. We have an unbalanced moment at B. Unbalanced moment at B. And that is equal to negative 7.5 kip feet. And then we distribute using our distribution factors. So I'm going to say distribution factor BA times positive 7.5 kip feet, which would give me a positive 3.8 kip feet. Distribution factor of BC times 7.5 kip feet, again, gives me 3.8 kip feet. And then we're going to carry over. We're going to say 0.5 times 3.8 kip feet. And then again, 0.5 times, oh, that should be an 8. .5 times 3.8 kip feet. And just doing a little bit of rounding, I'm getting 1.9 kip feet, 1.9 kip feet. And going ahead and populating my table now. That 3.8 that I just calculated, that was these two 3.8s. There's two of them there. And then half of one of them got sent over here as 1.9. And then the other on the right side of B, this one gets sent over to C as 1.9. Okay, now at this point, I would say is probably a good stopping point. All right. I normally stop iterating. We can say terminate iterations when values are approximately 10% within moment balancing. This would be fantastic in an Excel spreadsheet because you could just drag it down, however far you want. But once you've gotten pretty good closure, you would say sum of the moments here equals, and you would sum vertically down, okay, including the fixed in moments. You include the fixed in moments. So let's look at the moment at A first, negative 112.5. And I'd say plus 9.4, plus 10, plus 1.9. So I get, add that up one more time. Negative 112.5, plus 9.4, plus 10, plus 1.9. Yeah, I'm getting negative 91.2. And then again, add vertically here, including the fixed in moments, positive 112.5 plus 18.8 plus 20 plus 3.8. I get a positive 155.1. And then add vertically here. And I'm going to get negative 150 plus 18.8 minus 39.9 plus 20 minus 7.5 plus 3.8. And check this out. I got negative 154.8. Okay, so check these two values out. They are very close in magnitude to one another, and they have the opposite sign. That's what you want. If we iterated a few more times, these two numbers would get even closer and closer to each other. So that's what you want to get within 10% or even lower if you're doing this in a spreadsheet format, tolerance within each other, okay? So if we looked at like a percent difference, maybe we could say 155.1 minus 154.8. And then we could say maybe divide by the average, 155.1 plus 154.8 divide by 2, and you're within a really tight tolerance, like, you know, less than a percent. So you know, I say 10%, but even with these iterations, we went, you know, really close. So let's add up these values right here. We say 150 plus 9.4 minus 79.7 plus 10 minus 15 plus 1.9, 76.6. And then on the other side, negative 79.7 plus 20 minus 15 plus 3.8. I got, see, this one was a bigger difference from what I just got. I got here negative 70.9. Okay, I'm going to add those up one more time, make sure I didn't make a boo-boo. Negative 79.7 plus 20 minus 15 plus 3.8. Yeah, negative. So notice that these are not as close together. They have a bigger percent difference. And then when you add these up over at the roller, we balance that last, so that should be 0. So these are our moments right here. These are our internal moments, okay? So what you would do now is you would draw a free body diagram, and you would apply these moments to solve for the external reaction and reactions, and then draw shear moment diagrams. And we're going to do that in the second part of this example, which will be a separate video.